Starting again, symmetry. Huge disclaimer right off the bat. I've told you repeatedly, try not to use view and example. You got to get past view and example and be able to do these problems on your own. But especially, you don't want to use view and example on this. View and example is going to make it much more difficult than we want the problems to be. We are going to do symmetry just visually. Just looking at graphs. If you click on view and example, they're going to do all these algebraic tests with x's and y's and simplifying stuff like that. That's beyond what we want to do. We are just doing it visually. So a graph is symmetric with respect to the y-axis, or has y-axis symmetry, if the graph reflects across the x-axis. Shown below, the graph shown below has x-axis symmetry. It's as if the x-axis cuts the picture in half, or you could fold the picture along the x-axis and the two halves would lie on top of each other. A graph is symmetric with respect to the y-axis, or has y-axis symmetry if the graph reflects across the y-axis. The graph shown below has y-axis symmetry. The y-axis seems to cut the picture in half, or I could fold it along the y-axis. So those two are pretty easy to see. The last one's harder to see. A graph is symmetric with respect to the origin if the graph reflects across the origin. That's what you get. Doesn't help a lot. The graph shown below has origin symmetry. Origin symmetry is a double flip, so to speak. So here I could flip it across the x-axis, they would lie on top of each other. Here I could flip it across the y-axis, they would lie on top of each other. Origin symmetry is a quote-unquote double flip. Meaning this, or that I can take whatever's in, say, the first quadrant, flip across y, flip across x, first will land on top of third. And the same thing with second and fourth. I can take whatever's in the fourth quadrant, flip across x, flip across y, they will lie on top of each other. So I'm just going to take what's in the fourth quadrant and do my double flip. So I'm going to start here, start with this, flip across x-axis, result in red. Result in red. So if I flip this across the x-axis, it's going to look something like that. Then I'm going to take this part. So there was number 1. 1. 2. Flip across y-axis, result in green. So now I'm taking this red part, flipping across the y-axis, and there it would be. So there's my double flip. I took blue, flipped it across the x, got red, took red, flipped it across the y, got green. And then you could do the same thing with the first and third quadrants. And it doesn't matter if you do flip across x, then y, or y, then x, but it's a double flip. Origin symmetry is that double flip. And that's how we're going to do symmetry. We're just going to look at the pictures. So, looking at some pictures. Determine whether the graph of each equation is symmetric with respect to the y-axis, x-axis, the origin, more than one of these or none of these. That you can have no symmetry, more than one. So if I look at this one, this first one has just y-axis. And that's all it's got. The y-axis cuts that picture in half. It certainly can't have x-axis symmetry because there's nothing below the x-axis. And origin symmetry is always, as we saw here, fourth quadrant ending up in second quadrant, first quadrant ending up in third quadrant. Fourth quadrant, flip, flip, second quadrant, first quadrant, flip, flip, third quadrant. There's nothing in the second or fourth and third quadrants, so just y-axis symmetry. Okay, this next guy, and he's a little hard to see, so there's the graph. It doesn't fold across the y-axis. There's the y-axis. It's also not going to fold across the x-axis. And it's not going to do the double flip thing. And so there is no symmetry here. Can't fold it across the y, can't fold it across the x, and the origin symmetry, think opposite quadrants. First goes to third, second goes to fourth. I don't know if that's opposite quadrants, but, diagonal quadrants, we'll put it that way. This one, yeah, it would fold across the y-axis. It would fold across the x-axis. And first quadrant, flip, flip to third quadrant. Yes, I would have that. Fourth quadrant, flip, flip to second quadrant. This has all my symmetries. Next one, wouldn't fold across the y-axis, so it doesn't have y-axis symmetry. It would fold across the x-axis, so it has x-axis symmetry. And then the origin, again, think about those diagonal quadrants. First, flip, flip to third. Second, flip, flip to fourth. And first, flip, flip to third, those aren't going to look the same at all, so no origin symmetry. Then the last one, doesn't fold across the y-axis, so no y-axis symmetry. Doesn't fold across the x-axis, so no x-axis symmetry, but origin. If I envision flipping that across the y-axis, then cross the x-axis, it would have origin symmetry. And that's all we're going to do is symmetry. And again, emphasis, do not click on view an example. We are not doing it their way. Now what we're going to use symmetry for is to extend this to a property of some functions, which are even and odd functions. A function is even if f of negative x equals f of x for all x in the domain of f. So let's consider f of x equals x squared. And I'm going to find f of 3 and f of negative 3. So f of 3 will be 3 squared, which will be 9. F of negative 3 will be negative 3 squared, or 9. And notice the careful way I use parentheses. If you want to apply an exponent to a negative number, you have to put that negative number in parentheses. And so we have this. So f of negative 3 equals f of 3. And that's what this property was saying. F of negative x equals x. It's almost as if the negatives don't matter. That is an example of a function being even. It's as if the negatives don't matter. There's the graph of x squared. Notice it has y-axis symmetry. And so here's the fact that we're going to use. A function f of x is even if and only if it has y-axis symmetry. And again, here's another reason why you don't want to use view an example. That when you get to the even and odd homework on the computer, if you click on view an example, they're going to make it really, really hard. We're going to do this graphically. That we're going to look at the graphs, talk about the symmetry, and let the symmetry guide us about even and odd. A function f of x is even if and only if it has y-axis symmetry. So there's our fact for even and odd, for even. The flip side, odd. A function f is an odd function if f of negative x equals negative f of x. It's as if the negative factors out. It's not what's happening, but it kind of looks that way. So let's let f of x equal x cubed and find f of 2. So 2 cubed, which would be 8, and f of negative 2, which would be negative 8. And so I've got these things being opposites of each other. And so we do get that f of negative 2 equals negative 8, which equals negative f of 2. that f of 2 is positive. Now you don't have to worry. I know that's confusing some of you, and I don't really know much except how to do it. Well, we'll try it this way. F of 2 is negative 8. So then I just still have that negative, and then remember what f of 2 is. F of 2 was 8, so I leave my negative there, so that's the same little negative. Get rid of my hand here. So f of 2 was negative 8, and so I'm going on my next statement, so I still have that negative there, but then f of 2 was 8, so instead of writing the 8, I write f of 2. And not too important to remember that, not important at all. But my point here is that f of x equal to x cubed is an odd function. There's the graph of f of x equal x cubed. Notice it has origin symmetry. And so the fact we are going to go with is right here. A function f of x is odd if and only if f of x has origin symmetry. Again, do not press view an example here. They're going to make things so much harder than we want them to be. When it talks about even and odd, we're going to look at pictures, analyze the symmetry, and let the symmetry tell us about even or odd. It's odd if it has origin symmetry. It's even if it has y-axis symmetry. Okay. Use possible symmetry of the graph to determine whether it's an even or odd function or the function that has neither of these. So I see that picture. It has no symmetry. It doesn't have y-axis symmetry. It doesn't have origin symmetry. It doesn't have x-axis symmetry. And since it has no symmetry, it's neither even nor odd. Here, I'm just warning you, don't use view an example. I've already warned you a couple times. So, determine whether each function is even or odd. Then determine whether the graph is symmetric with respect to the y-axis or origin or neither. When you read those instructions, immediately graph it. Graph to answer. And so you're going to need a graphing calculator. If you don't have a graphing calculator, go on some sort of computer and go to a graphing website, but we do need to graph it somehow. And come test time, you're going to want access to a graphing calculator. Should you buy one? That's up to you. If you have to take survey of calculus, you probably will want one. You probably will want a graphing calculator. If you don't have a graphing calculator and you're not afraid to go into a pawn shop, I've been told that pawn shops sometimes have graphing calculators at ridiculously low prices, or borrow one from a friend. But what we're going to do first on these guys is to graph them. And that's what we will do on the very next video.